Hi everyone, welcome back to Chem Story. Today we're diving into one of the most powerful tools in alkyne chemistry, acetylide anions. These guys are small, but they open up big opportunities when it comes to building carbon-carbon bonds. So in this lesson, we'll look at how acetylides are formed, what makes them unique, and how they show up in key reactions. Alright, let's get into it. So let's start with this. How do we actually get an acetylide anion? It all comes down to the acidity of terminal alkynes. Take a look at this comparison. If you line up a terminal alkyne next to an alkene or an alkane, you'll notice something interesting. The alkane has a pKa of about 25, while the alkene is way up at 44, and the alkane even higher, around 60. That tells us terminal alkynes are much more acidic than the other two. And why does that matter? Because the more acidic a proton is, the easier it is to pull off. And that's what lets us turn it into a reactive anion. Now let's talk about why alkynes are more acidic than alkenes or alkanes. It all comes down to the type of orbital that holds the lone pair on the conjugate base. Here's the trend. In an alkane, the conjugate base is sp3 hybridized. That's only 25% S character. In an alkene, it's sp2, so 33% S character. But in an alkyne, the acetylide anion is sp hybridized, and that means 50% S character. Why is that important? Because the more S character an orbital has, the closer it pulls the electrons toward the nucleus. And when those electrons are held tighter, the anion becomes more stable. So to sum it up, acetylide anions are more stable than alkyl or vinylic anions, and that's exactly why terminal alkynes are more acidic in the first place. Now let's zoom in on how acetylide anions actually form step by step. We start with a terminal alkyne, meaning there's a hydrogen directly bonded to one of the carbons in the triple bond. That hydrogen is relatively acidic, with a pKa around 25. So if we hit it with a strong base, that base uses its lone pair to grab the proton. As the proton leaves, its electrons slide back onto the carbon. And that's how we end up with a negatively charged carbon, also known as the acetylide anion. And here's the key part. That carbon is now a strong nucleophile, ready to attack electrophiles in the next reaction. So what can we actually do with this acetylide anion? One of the most useful reactions is nucleophilic substitution, more specifically SN2 with alkyl halides. Here's how it goes. The acetylide acts as a strong nucleophile. It attacks the electrophilic carbon in the alkyl halide and kicks out the leaving group in one smooth, concerted step. That's your classic backside attack. Exactly what you'd expect in an SN2 reaction. And the result? We get a brand new carbon-carbon bond, which is a big deal. It means we can extend carbon chains by connecting the alkyne to another carbon piece. Whether you're working with a primary halide or something like a benzylic halide, as long as the setup is right, this reaction gives you a really powerful way to build up molecules. Now here's something you need to watch out for. If you try to react an acetylide with a tertiary alkyl halide, like 2-bromo-2-methylpropane, things don't go as planned. You won't get substitution. Instead, you get elimination. And why is that? Because tertiary carbons are way too bulky for an SN2 attack. There's just not enough room for a backside approach. So the acetylide ends up acting as a strong base, not a nucleophile. It pulls a proton off the beta carbon, and that triggers an E2 elimination, giving you an alkene instead. So here's the bottom line. With primary alkene halides, acetylides go SN2. But with tertiary halides, they shift gears and go E2. Now let's check out another super useful reaction, the attack of acetylide anions on epoxides. This one's great because it lets you extend the carbon chain and add a functional group in one step. Here's how it works. The acetylide acts as a nucleophile and attacks the epoxide, kind of like an SN2 backside attack. The acetylide targets the less substituted carbon because it's more open and easier to reach, with less steric hindrance. Once the ring opens, we usually add water or a dilute acid to protonate the oxygen, and that gives us an alcohol right where the ring used to be. It's a super efficient way to make new carbon-carbon bonds, and you end up with an alcohol group that's perfect for doing even more chemistry down the line. Now we're stepping it up a bit. Let's talk about the alkylation of dianions. This starts with a special kind of terminal alkyne, one that has another acidic hydrogen right next to the triple bond. If you treat it with two equivalents of a strong base, like N-butyllithium, you can pull off both of those protons, one from each carbon. That gives you a dianion, a molecule with two negative charges, one on each carbon. It's super nucleophilic, and just like before, it can react with alkyl halides. So if you add something like methyl iodide, the lone pair on one of the carbons attacks the electrophilic carbon on the halide, and boom, you've got a new carbon-carbon bond. After a quick aqueous workup, you end up with a clean product, an extended alkyne that's ready for the next transformation. If we take a closer look at the starting molecule, you'll notice it has two acidic hydrogens, one at the terminal carbon and another right next to it. Now, even though both of them are acidic, they're not exactly the same. There's a slight difference in their acidity, but what really matters is this. The conjugate bases that form after deprotonation don't behave the same way. They have different levels of nucleophilicity, and that leads us to the key question: which proton gets removed first? And which of those conjugate bases ends up doing the nucleophilic attack? That's what really drives how this reaction works, and why it's such an interesting example. So first, we treat the molecule with N-butyllithium. The first equivalent removes the more acidic terminal hydrogen, just like in a regular acetylide formation. Then, with a second equivalent of base, we can deprotonate the neighboring hydrogen as well. And now we've got a dianion, with two negatively charged carbon atoms, side by side. Next, the second carbon ion, the one formed at the sp3 hybridized carbon, reacts with an alkyl halide, like methyl iodide. And why is this carbon so nucleophilic? Because it's the conjugate base of a weaker acid, which makes it more basic and more eager to attack an electrophile. So the more nucleophilic carbon goes after the alkyl halide, attacking the electrophilic carbon and kicking out the leaving group, forming a brand new carbon-carbon bond. Then finally, after an aqueous workup, everything gets protonated, and we're left with a nicely substituted alkyne. It's a great example of how strong bases, smart use of acidity, and a good understanding of nucleophilicity all come together, letting us turn simple starting materials into more complex molecules. And that wraps up our look at acetylide chemistry. We explored how they're formed, how they react with alkyl halides and epoxides, and just how powerful they are for making new carbon-carbon bonds. Thanks for watching, and I'll see you in the next Chem Story video.